Welcome to chapter 22. We're going to do carbonyl condensation reactions. So this comes after chapter 21 on enolates. And carbonyl condensation reactions are kind of combo reaction that uses the carbonyl as the electrophile and also as the nucleophile. So we learned when we first did carbonyl chemistry that this carbon here is electron deficient, so a nucleophile can come in and attack, and if you have an aldehyde or ketone, then you get this addition product. If you have a carboxylic acid derivative with this leaving group, then the nucleophile will come in and then displace the leaving group and give you a substitution product instead. So this is with the carbonyl as an electrophile. Then in the last chapter, we learned that you can deprotonate the carbonyl with a strong base, right? The alpha protons. Once you do that, you get this enolate, right? This resonance structure of the enolate, which then itself is the nucleophile and will attack an electrophile that you give it. So, what happens if you generate an enolate in the presence of a carbonyl, right? The enolate is a nucleophile. If you have a carbonyl that has not turned into an enolate, then it is still an electrophile. So the nucleophile will attack the electrophile, right? And you will get this addition product. You'll notice that the nucleophile ketone is intact, but the electrophile has turned into a single bond here, right? Now I can quench this addition product and stop there with ketone and an alcohol, or I can push this further and get a condensation product by basically removing H2O, right? I lose H2O, and this gives me this condensation product. This is important because this is an irreversible process. Right? Whereas the addition product, right, can be reversible. And so by forming the condensation product, you remove the addition product from your reaction pot, right? And by Le Chatelier's principle, this pushes this reaction forward towards the addition product and then to condensation. So forming the condensation product will sometimes let you push these reactions forward. But in these condensation reactions, you have an addition first and then a condensation. Here are all the condensation reactions that we're going to cover, but don't worry, a lot of them are basically very similar and use the same mechanisms that we've already learned for carbonyls and enolates. Now, here is sort of a list of all the ones that we are going to learn in this chapter. The aldol is the most important, the first one we're going to learn. A straight aldol is with two of the same aldehyde and ketone. So they're the same, there can't be any mixing, and because they're aldehydes or ketones, you're going to get acyl addition. A crossed aldol is when you have two different carbonyls, say an aldehyde and a ketone, or two different aldehydes, and then who can be the nucleophile, who can be the electrophile gets confusing, right? And then you get a mess of products. To avoid that, we're going to learn how to do the directed aldol. Again, two different carbonyls, so maybe two different aldehydes, but we're going to do it stepwise. So we form our enolate, then add our electrophile, and that will avoid the mess. Then we're going to cover the claisen reaction. The claisen reaction is exactly the same as the aldol, but instead of ketones, we're going to have esters. Because they're esters, carboxylic acid derivatives, they will perform acyl substitution instead of addition. So that'll be slightly different. And then the last two reactions are the Michael reaction and the Robinson annulation. And those will be the reactions of enolates and a conjugated carbonyl. So now we're going to get conjugated addition. We'll see that at the end of this chapter. Let's start with the aldol. So, as I said, the aldol uses two of the same structure. In this case, aldehydes or ketones. One will be the electrophile and one will be the nucleophile, but they are the same. The product you form is called a beta hydroxycarbonyl. Beta because this is the alpha position, this is the beta position. So you see we have a beta hydroxy, beta to a carbonyl. So that's where the beta hydroxy comes from. We're going to use NaOH, an aqueous NaOH, and let's look at the mechanism. So here we're going to have, this is going to be a weak weak nucleophile, so this will be a reversible mechanism. We're going to start with the alcohol, the base deprotonating the alpha CH and forming the enolate. So our first structure is, there's still one proton here, right, is the enolate. And this has a resonance form. I don't always draw it, but right, this is the enol form, and this is the keto form. So once you have your enolate, it can react with an electrophile, and the electrophile is going to be the same structure, your original starting material. Now you can draw the enolate attacking, or you can also draw from the enol form attacking. It's the same. You attack the carbonyl, and you will get an initial addition product. Oh, I'm forgetting an R group. Here we go. So we have a new CC bond that's formed here. And to get the final addition product, you would quench with water to get the actual beta hydroxy alcohol. Now I want you to notice that this aldehyde or ketone, right, has not changed. It's from the nucleophile, but our alcohol here is from our electrophile, right? So I recommend always drawing your beta hydroxy product in the same order. Put your nucleophile group that hasn't changed here, and then always like alpha, beta, alcohol, right? Always draw it in the same way, and that will help you always draw the right structure for the beta hydroxy. Okay, let's try some practice problems. Now I'm going to put practice problems in the slides like I do in lecture, but please pause the video, give these a shot before watching me dive into them, right? Okay, let's look at this first one. Which of the following could be a product of an aldol addition? basically they're asking us to identify which one is a beta hydroxy product. Right? So we're looking starting from the base of our ketone. This is alpha, and oh, the alcohol is already there, so that's not a beta hydroxy product. This one, here's the base of our ketone. This is the alpha position, and this is the beta position. And hey, the alcohol is there. So this could be a product of an aldol addition. Let's do this one. That's the base of my ketone. Here's alpha, here's beta, and here's gamma. Gamma is not a beta hydroxy product, so this one could not be an aldol addition product. All right, draw the mechanism for this reaction. So we know that there's going to have to be two, right? We're going to first form the enolate. So there are protons here. Our base is going to come in, deprotonate, and form an enolate. This is all reversible. So there's our negative charge. Now this is where we have a second one of our starting material, starting molecule, that's going to act as the electrophile. So now our newly formed enolate is going to come in and attack another one of the same aldehyde. Again, I like drawing the beta hydroxy product always the same. So here's my beta hydroxy. Actually, I'm getting ahead of myself. It should just be the O minus, okay? But now let's fill in all the parts that are missing, right? So off of my original aldehyde is this phenyl group, like this. And then this is also 1,2-phenyl off of this group. Now I can quench, and in this case I'm quenching with ethanol. That's the solvent that's here. It's not aqueous. Remember, nucleophile attacks electrophile. And then my final product is the beta hydroxy. Here is that new CC bond. Okay, let's do some retro-aldol. So here is a possible aldol product, and we're going to go back and find the carbonyls, either aldehydes or ketones, that were used to form it. So you start at your carbonyl that's still in the product. This is alpha, this is beta, and this is where you're going to split, right, between the alpha and beta position. So what could have made these? So one of them, kind of going to draw it in the same, so one of them was this enolate here, and the other one was this aldehyde in this position, right? But these are exactly the same compounds. Here is this oxygen and this ketone still here. Okay, let's do it again for this structure. We start at the base of the carbonyl. This is alpha, this is beta. So we split down the middle between the two. Our enolate was this one, and it would have reacted with this aldehyde here. So again, this oxygen is this oxygen, and the nucleophilic ketone stays untouched. Now, when we look at aldol reactions with aldehydes versus ketones, we see a pretty big difference. Now, aldehydes and ketones have very similar reactivities as nucleophiles, but aldehydes favor the aldol addition, whereas ketones do not. So with aldehydes, this will be easily formed, they're very reactive, but with ketones, it will be harder to form this product. Why? Because aldehydes are better electrophiles. And we learned this when we first studied aldehydes and ketones, right? Aldehydes are unhindered, whereas ketones are hindered, right? They have more R groups around the electrophilic carbon. The aldehyde is also more electrophilic, right? To be electrophilic, you want to be electron poor, and the aldehyde only has one R group helping it out, donating electron density, whereas the ketone group has two R groups donating electron density. So it's still electrophilic, but it is less electrophilic. So that makes ketones less reactive in an aldol reaction. They're less likely to be attacked by an enolate when the enolate is formed, whereas aldehydes will get attacked readily. So if you've made your, if you want to make the ketone condensation product, right, you can help push this forward by doing the dehydration. Now, the dehydration is irreversible, right? Once you go here, you do not ever go back to the aldol addition, and you never go back to the ketones. So you have to really want to get this final product. You go from your beta hydroxy carbonyl to a alpha beta unsaturated carbonyl, right? Here's our carbonyl. This is alpha, this is beta, and we have this unsaturation there. So that's why it's called an alpha beta unsaturated carbonyl. You can do this reaction in acidic conditions or basic conditions, but you do need heat, okay? So heat is that hint that tells you that we're going to a condensation. If you don't see the heat, then you're probably stopping at the aldol addition product. So let's look at the mechanism with an acid. So with an acid, this alcohol will be protonated first. So we will get this structure, right? And then we will deprotonate this alpha hydrogen, right? H2O now is here, we'll deprotonate here, and that electron density will form the double bond, and at the same time you eliminate water, right? So this is your elimination of H2O in one step, and your resulting product is your unsaturated carbonyl, like that, plus H2O that you have kicked off. Now let's do it with a base. So with a base, you're not going to touch this alcohol. Instead, you're going to go straight to the deprotonation, right? This, oops, let me do it pink. This base will deprotonate here, you will form that double bond, and it's an OH minus that will be your leaving group. And so you form your unsaturated carbonyl right in one go, plus water that you formed with your base, and then you regenerate some base as your leaving group. Okay. Again, urge you to practice these at home before watching the video. So it's telling us what unsaturated carbonyl compound is formed by the dehydration of each of these. So dehydration, right, always base or acid, and heat, always heat. So the thing to do is find your carbonyl, find alpha, find beta, and then you're going to lose this alcohol and you're going to form that double bond in between your alpha and your beta. So A would then be this. B again, so this is an aldehyde here. So this is alpha, this is beta. I'm going to form that double bond there. And C, carbonyl, this is alpha, this is beta, so it's going to be here. Okay, let's look at a crossed Aldol reaction. A crossed Aldol reaction means that you have two different ketones or two different aldehydes mixed in the same pot. You add a base and you let fate decide who's going to become the nucleophile and who's going to become the electrophile. Now, doing that gives you a lot of different combinations. Let's call this guy 1 and this one 2. So maybe 1 becomes the nucleophile and attacks another 1. Maybe 1 is the nucleophile and attacks 2. Maybe 2 is the nucleophile and attacks another 2. Or 2 could become the nucleophile and attack another 1. You can sense the mess already. I urge you to draw these always the same way. So I always like to draw my beta hydroxy like this, and then kind of fill in the pieces after, right? So if this is a 1, I have a group here and an ethyl here. This is a 1 attacking a 1. Now let's do a 1 that attacked a 2. So that's just a methyl group. If it's a 2 that attacked another 2, then you get that. And if it's a 2 that attacked a 1, this is ethyl, right? So let's see the 2 oxygens, here's 1, another 1, and here, and the 1 oxygens here, here, and here. Now all of these can undergo condensation reactions, so let's draw them out. Let's see. We can have double bond here. Oops, not there. Here. You can have like this. Or like this. Okay, so you have 4 products at the end, and these are not easy to separate, so this is an absolute mess. This is not a great way to do an aldol reaction. So what would you do instead? There are a few safe crossed aldol reactions. A safe crossed aldol is when you mix them both together, but one of them cannot become your enolate. For usually the most obvious reason is that it has no alpha CH, right, to deprotonate. So it cannot form an enolate. Also, usually aldehydes are the better electrophiles. So if you can get a aldehyde that cannot be enolizable, right? So here, no alpha CH. Here as well, this benzene ring, right? That compound cannot become the enolate. So what else is in the pot, right? This will be an enolizable ketone, and so that's going to be the only enolate present. So that can pretty safely do the addition this way. Remember, you can enolize alpha to a nitrile, right? And then with heat, you get your condensation reaction. Okay, what keeps the enolate from attacking itself, though? Ideally, you choose a ketone because those are less electrophilic than the aldehydes, so they won't compete as much. So there's a low chance of self-attack. Right. So those are little tricks you could use to do a safe crossed aldol and mix everyone in the pot. But a even safer method is the directed aldol. In a directed aldol, we're going to do things in 2 steps. First, we're going to take the compound that we want to make the enolate with. All by itself, we're going to add a strong base, and then we will get a quantitative amount of our enolate. Now, if we use LDA, right, remember this is a bulky base, so we will get the kinetic enolate. If we use an unhindered base, then we'll get the thermodynamic enolate. It's best to use a strong base though, because you want this to go all the way to the enolate, right? So you do want a strong base. Once you have your enolate made, and that's it, there's no more base left, then you can start to add your electrophile. And in this case, the aldehydes are good electrophiles, but you could add whatever you wanted. There's no more base to make enolate, so this will be selective. Only your pre-made enolate will be the nucleophile. So yeah, you add the electrophile after all the enolate is made. And that gives you that selective addition, and so no mess, right? You should only get one product. Let's look at what that looks like. So we're going to take 2 different paths. We're going to do the bulky base and the unhindered base. So we're going to get our kinetic enolate and a thermodynamic enolate. Let's do LDA first. That's bulky, so that's going to be my kinetic enolate. Like that. That's all formed. I'm adding my electrophile. Now again, I urge you to redraw your beta hydroxy always the same way. So this is my nucleophile. I'm going to draw it back this way. And now my electrophile had a CH3 and 3 carbons here. 1, 2, 3. Okay, and I had water, so that's why I get my quenched aldol product. Now if I add acid and base, and importantly heat, I can get my condensation product, and that looks like this. Right? Okay, let's do it the other way. Now I'm going to add NaH, so I'm going to get the thermodynamic product, which is this enolate. Again, same electrophile. I still like to draw my beta hydroxy in the same direction, but now remember my enolate has changed. So here I have this, and what's on my electrophile, same thing, 1-methyl and then the 3 chain. Okay, now can I proceed and add my base and more acid or base and some heat and get the condensation product, right? Can I do that? The answer is no reaction, because I have to eliminate a hydrogen, but there is none there, right? There are no alpha CHs, left to, so right? So that means no elimination possible. So that just stops at the aldol addition product. Here's a little practice for you, just this little one. So pause, do it. Yes? Okay. So my ketone here is symmetrical. This doesn't really matter that I used LDA, but I'll form that enolate. And then we're going to attack this aldehyde as my secondary electrophile. And remember to reorganize. So this is just methyl ketone, and then here I had H and 1, 2, 3. Right, so this would be the product of the aldol addition. Okay, now intramolecular aldol condensations. We'll see a lot of intramolecular reactions. So in this case, there's also going to be a competition between who's going to be the electrophile and who's going to be the aldehyde. Usually the electrophile is the aldehyde because, as we said, they're more electrophilic. I cannot talk and write at the same time. So if there is one, that's going to be the electrophile. Basically, whoever is more electrophilic. Now with the nucleophile, it's gonna depend on the base, right? So if we have our a weak base or unhindered, right? So this is referring to an NaOR or OH or NaH, right? Is the unhindered base. That will give you the thermodynamic enolate. And if you use a bulky strong base, basically LDA, then you'll get the kinetic enolate. But there's another factor at play, and that this really works well for 5- and 6-membered rings. So if you try to force it with like a bulky base to make a 4-membered ring, that's not going to be as favored actually as making the 5 to 6 membered ring. So you want to match your cycle, right, like your base to the right cycle size. So in this case, with like NaOH, right, this would be a weaker base, so this gives us the thermodynamic enolate here. Then this would attack our aldehyde, and then you just write out your carbons, right? 1, 2, 3, 4, 5. So in our cycle, this is 1, 2, 3, 4, 5. And again, if you add heat, then you can get the condensation product. Okay, let's do some practice. Okay, now here we have a variety of hydrogens that we could deprotonate. We could deprotonate over here or over here. Remember, these between two ketones, right? These are the most acidic. So this will definitely go first. So our enolate is going to be this one, right? And then 1, 2, 3, 4. So now our aldehyde on the end, that's going to be the electrophile, get attacked. So let's count 1, 2, 3, 4, 5, 6. Great, 6-membered ring, definitely favored. I'm just going to go ahead and draw a straight 6-membered ring. I'm going to label it 1, 2, 3, 4, 5, 6, and then match who's where, right? 6 was an alcohol from my aldehyde, 2 ketone left, still there, and then off of the 1, we've got an aldehyde. Right, so that's the product for this one. Let's try the next one. Now this one is symmetrical, so I could form an enolate here or here. It would be the same. Let's draw one here. Now if I go ahead and make this intramolecular like this, let's count my carbons, 1, 2, 3, 4. That's pretty tight. That would be basically 1 would have an aldehyde off of here, and 4 would be my alcohol. Right, this is a 4-membered ring that's highly strained. So if I make this at all, it would be a minor product. In this case, what's more likely to happen is that this molecule simply finds another molecule in the pot and attacks over here. And instead of getting our cyclic product, we end up with and then here again, 1, 2, 3, 4. There, that's my aldehyde, sorry, over there. Right, so instead, this would be the major product. Okay, we have some more practice. Okay, definitely try this a little bit at first. Let's go, okay, A. Okay, we're going to do an intramolecular aldol, nice, they tell us, and then a dehydration. So dehydration, base and heat. So here we have an aldehyde, and so the aldehyde is going to be our electrophile, the ketone is going to be the nucleophile, because the aldehyde is the better electrophile. And I kind of have the option, I could make one here or here. They don't really tell us where I'm making, like what base they're using. And in this case, you would probably get a mixture of both these enolates. These are both possible. But this one would form a tiny ring, right? So that won't be good. So instead, I'll do this. So again, counting the carbons helps. 1, 2, 3, 4, 5. So I'll just draw a 5-membered ring. That's not a 5-membered ring. Like this. And just number them. 1, 2, 3, 4, 5. Okay, so 1 had my methyl group off of it. 2, the ketone, and then 5 was my alcohol from the aldehyde. If I do dehydration, let's say base and heat, then I lose the alcohol, and that's my dehydration product. Okay, B is easy. They are symmetrical. Let's say we form that nucleophile on this side and then attack the aldehyde on that side. Let's count the carbons. 1, 2, 3, 4, 5, 6. Okay, so I know right off the bat I can draw a 6-membered ring. 1, 2, 3, 4, 5, 6. And let's see, at 1 I have another aldehyde that's still there, and at 6 I have the aldehyde that turned into an alcohol. And again, with base and heat, then I would get the dehydration product like that. Okay, C is kind of messy. Bear with me here. So there's a lot of different enolates that could be formed. You could have this charge over here, and that could attack over this way. You could have this charge over here, and that could attack that way. And then similarly, negative charge on this side could attack, or negative charge on this side could attack. If you run through them, you'll notice that some of them give you 4-membered rings, so that's no good, and 2 will give you a 5-membered ring, and they're symmetrical. So we'll do one example that gives you a 5-membered ring. Sorry. Okay, so let's assume we make this nucleophile, and this one attacks here. Now in my ring that I'm making, I have 1, 2, 3, 4, 5 carbons. So let's start with that. But then out of that ring, let's see, let's make one. Well, 1, 2, 3, 4, 5. Okay, so 1 has my ketone coming off of it. Oh, I drew this backwards. Okay, and 5 has my alcohol. But now, let's draw it this way. Okay, so now between 1 and 5, well, between my ketone here, 1, 2, 3, 4, 5 to this spot as well, okay? So 1, 2, 3, 4, 5. That makes that clear, right? 1, 2, 3, 4, 5. Okay, so this is actually, let's maybe redraw this better. So that actually makes a 6-membered ring. 1, 2, 3, 4, 5, and then this was my original 5-membered ring. And with base and heat, we get that as the condensation product. So in this case, we were making 2 cycles. Both of them were 5 or 6, so that's okay. D is just a little bit tricky to see. This is going to be my enolate. Can't form an enolate here. There's no spot. And I'm going to attack this ketone. So you can kind of draw it flat, right, where this becomes an alcohol. This side has this ketone, and then with methyl group, and then that attacks, that's connected there. Or you can kind of redraw this kind of like this, with the alcohol on this side and then the bridge going over, and then the bridge has a methyl group and a ketone. So you draw it differently, but that's what it looks like. Okay, after this, so now we're going to do the claisen condensation. So the claisen condensation, so I'll move this guy away, is basically an aldol with esters. The mechanisms are really similar, but these are esters, so they are carboxylic acid derivatives, and they have leaving groups. So what's going to happen when one of them attacks, if one of these acts as the nucleophile and attacks the electrophile, instead of getting an aldol addition where you get an OH, right? Instead, we're going to boot off this leaving group. So let's see what that looks like. So first we're going to deprotonate. The base is going to deprotonate and form our enolate. Like that. And now we're going to add another one. Again, now this is a straight claisen, so it's going to be the exact same molecule. It's going to attack, this breaks that double bond. And then we get our tetrahedral intermediate. So O minus, O methyl, and another, that RR group over there. So instead of staying at this sort of addition product, this will come back down and kick off our leaving group, right? This is our leaving group. And now it is very important that you don't miss this next step. So you think, oh, I'm at my product, I'm done, but I'm not. This is a very acidic hydrogen, and I have just generated this leaving group, right? Good leaving group, but also very strong base. So there's no way it's going to leave that proton there. So it will deprotonate, and this is an important step because it kind of drives the whole reaction forward. A lot of these are all reversible, but this is a fairly strong, it's not completely irreversible, but this drives this reaction forwards. because you form this very stable enolate, right? So by Le Chatelier's principles, you're forming this product that's sort of pulling the whole reaction forwards, right? So this is the end product that pushes reaction forward. So yeah, so this is very stable, right? Because it has two resonance structures with both ketones. And then you get, you're happy, your methanol is formed again. So that's why you have a second step, which is the quenching step. So usually an acidic workup. So this is where you quench. And then you have your actual product. Now, you might say, okay, this is the same as this. Why do I care? Like, sure, quench, right? But it's actually very important to understand that this product must be formed. And for this product to be formed, this proton needs to be present. What does that mean? Going all the way back here, this proton is important. He's not deprotonated at the beginning, but he is actually key. So in your starting nucleophile, you need 2 alpha CHs. Absolutely need 2. If you don't, the reaction actually doesn't go. The esters are more stable on their own, and there's nothing that drives the whole reaction forward. There's another weird thing about the claisen reaction that you have to remember is that all of the OR groups have to be the same, ideally the solvent too. Why? Right? Because as you might have thought when you saw this example, right, I'm going to add this base. Well, we've seen that reaction before, except like this, right, where instead of deprotonating, the base is the nucleophile and attacks the ester directly. And that is going to happen during a claisen reaction. You will make this tetrahedral intermediate, and it's true that, right, when this comes back down, it could kick off one of the leaving groups, but if your ORs are the same, that's okay because you just get back, you get back your starting material. Right, so it's very important to keep the OR groups the same. If you use mismatched base, then you get a scrambling. Of the ester groups, right? So you will, during the claisen, acyl substitution does happen. You just have to plan for it and make sure that you're not messing up your product as you do it. Okay, here's a little bit of claisen practice. They all are using 2, right, of the same, and you want to check that your R group matches. O-ethyl matches, yes, but what is missing here for our nucleophile? We only have 1 hydrogen here, not 2. So this is actually a no reaction, right? There is only one alpha CH, and you need to have both to favor the product. Let's do number 2. So now we're good. We have 2. Our O-methyl matches our base, so good. We're gonna deprotonate, form our enolate, and attack another ester. So O-methyl, and then that's going to be the product. This is a beta keto ester, by the way, right? So this is ester, alpha, beta. So just like before we had the beta hydroxy product, now we have a beta keto product. This last one, oh, it's gonna mess up, right? We have a base that does not match our ester group. So the reaction will go, right? But you're gonna get some of the right product, or maybe your intentioned product, but you're also going to get the same thing with the ethyl group, right? So you're going to get O-methyl and O-ethyl. You get a mix, which is unfortunate. Okay, here's some retroclaisen. So what are the components that are going to make this structure, and ideally what base do I want to use? So when you come up with the retro, find, first find your beta ketones. So you know, okay, this is a beta ketone, so I got to have some esters, right? So find one of your ester groups, then do alpha, beta, keto, and then break between the alpha and the beta. So what does that give me? Here's my first right, so this is going to be the enolate that I want to form. Right, this R group is this R group, and my other compound is the same, right? Basically, like that. And now, ideally, what kind of base would I want to use? I would want to have a matching base, so would be NaO cyclopentane here, and ideally I want to match my solvent as well. So I would want to use cyclopentanone. Pentanol as my solvent. Now, just like with the aldol, there are ways to do a safe crossed claisen. In this case, again, you want to have a non-enolizable ester, so basically have no alpha CH to make the enolate. So here it's just an aldehyde. Okay, that's not off the carbon, and here it's phenyl, right? There's no alpha CH. And then you mix this in with an enolizable nucleophile. So this one would be an ester that does have some protons. So this, So yeah, so these, do have the 2 alpha CHs. And to avoid having your enolizable ester attack itself, just a little trick is that you add it to the reaction very slowly. And in that way, it's always surrounded by an excess of your electrophile ester, right? And so then it's less likely to react with itself. Okay, so those are, again, little tricks to do a safe cross-claisen. Okay, next up is an intramolecular claisen condensation. It's called a Dieckmann reaction, but who cares? It's just an intramolecular condensation. Again, you're going to want to choose your nucleophile and electrophile to make the best ring, best sized ring, generally 5 or 6, right? That's what you want to be making. Your nucleophile still needs to have your 2 alpha CHs. That still needs to happen, and ideally all your OR groups need to be the same, right? But if you match all of these criteria, then you're good to go. Let's say make our nucleophile here. With esters, it's kind of nice. There's no thermodynamic versus kinetic because one side is the ester group. So that's one less thing to worry about. And then I count my carbons, 1, 2, 3, 4, 5. And that's how I make that 5-membered ring, right? 1, 2, 3, 4, 5. In this case, instead of the alcohol, right, this stays as the ketone, and I have my beta keto ester as my product. All right, this is a good one because it's an intramolecular, but also some mechanism to do. You'll notice that the molecule is symmetrical. So that's easy. I can choose either one of these to be my enolate, right? Both of these could become the enolate. I'm gonna go ahead and pick one. Let's see, our base is methoxy. I'm gonna take this one. So then that's my enolate. Sorry, you can probably hear my daughter screaming in the background. I swear, she's having fun. Okay, so then now I form this enolate. It's going to attack the second ester. And let's make the tetrahedral intermediate. It's really ugly, but that's actually it. And then this will come down and boot off that leaving group. Let's draw this a little bit better. Okay, but again, do not stop here. Do not stop here. we have to deprotonate this, right? We just made this. It's coming after that proton. And this is my mostly not reversible reaction that pushes everything forward. Okay, she's less happy now. And now that I have this enolate here, now I have to quench to actually get, for real, the final product. So this is with H+. Okay, so I mean just any water, some acid, that will be the nucleophile and quench it, right? So if we do a mechanism, right, you cannot overlook this step. You start overlooking this step and then you stop thinking that you need that second alpha CH, and then you start making reactions that are not actually correct. Now, we can actually combine an aldol reaction and a claisen reaction, and this opens up some cool new products that you can make. So if you use a ketone or aldehyde as your nucleophile, and then add the ester as the electrophile, then you can get a beta ketone. And if you use your ester as your nucleophile, but then add an aldehyde or a ketone as your electrophile, then you can get a beta hydroxy ester. So this gets you some new products by being able to combine the aldehydes and esters. And you want to do this in a stepwise method though, to control who is going to be the nucleophile and who is going to be the electrophile. All right, so here's some practice. First one, we have the aldehyde is going to be our nucleophile. So the way this is drawn, right, we start with aldehyde, then we add base first, and then we add ester. And I'm actually just going to add quenching step here. It's not drawn in, but then we want to quench. So I'm going to make this nucleophile. It's going to attack the ester, and then the ester is going to bump off the leaving group, and my product is going to be the aldehyde, and the ester is the electrophile. So this gives me that beta ketone product, and we're also going to have some methanol here left over after we quench. Right, so this is beta keto aldehyde. Oops. And our next one, now this time the ester is going to be the nucleophile. It's going to come here and attack this aldehyde. And now we don't have a leaving group, so we get an addition product. And the ester stays in place. And after we quench, we get this. And yeah, so this is the aldehyde, right? So there's one more proton here. So this is our beta hydroxy ester. Right. So just like we had before, right? Whoever is going to be the nucleophile gets to keep its carbonyl unit. Especially, but basically that unit is on the end unchanged. Okay, let's do kind of a retro. Find two pairs of carbonyls that will form the following product. This is a beta ketone, right? So what does that tell us? That means that the ester was the electrophile. If the ester had been the nucleophile, we would have an ester group still present somewhere, but it's gone. So that means that the ester was the electrophile. So in all of these splits, we're going to make sure that the nucleophile is the ketone or aldehyde. Okay, so we can split it two ways. We could split it here, or we could split it here, depending on who we count as the nucleophilic carbonyl. Let's look at splitting it that way. We have this group, and so this will be our electrophile, so that's going to be our OR group, our ester, and then the other half is going to be our aldehyde, right? So that's going to be our nucleophile capitalized is the ester. Now if we break it the other way, so we want to have this piece stay the ester, right? Well, it doesn't have to be methyl, it could be any ester. And our other half will be our nucleophile. So in this case, our nucleophile is a ketone, and our ester is still the electrophile. But both of these would work and form just that product if we did this stepwise. Okay, so really combining all the things, now we're looking at an intramolecular Aldol claisen. Again, we really want to make those 5 and 6 membered rings, right? That's still important. But now there's an added competition of who's going to be the nucleophile and who's going to be the electrophile. If you see that your product, like in this one, there is no ester group left, then the ester was your electrophile. It's a good hint. Also, who's going to become the nucleophile really depends on who's going to get deprotonated first to make the enolate. And remember from when we first looked at enolates, right? The acidity of this proton changes with the structure. So if you're between two ketones, you're really super acidic. And then if you're an aldehyde, you're very acidic as well. Ketone, very acidic, starting to be less active now with the donating groups, right? So the aldehydes and ketones are more acidic than the esters. Okay, so that means that they will form. So aldehydes and ketones form enolates much faster. really much faster. So in this case of an intramolecular, usually it's going to be, this is going to be the more acidic proton. So the aldehyde or ketone will probably be your nucleophile. And so if that happens, we get negative charge here. And then it's the same, right? Counting the carbons, 1, 2, 3, 4, 5, right? 1, 2, 3, 4, and 5. You lose your ester group, but you keep the ketone. Okay, so here's a little practice where we're trying to draw the two ways that we could form this structure, one intermolecular and one intramolecular. First, we look at it, it's a beta ketone, right? So the ester is the electrophile again. Now, let's look at the two ways that we can split it. We can split it this way or this way. Well, let me make that a different color. Okay, let's do the green first. So we would get this ketone as our nucleophile and this ester as our electrophile. If we split it up the other way, the orange way, we would open up this ring, right? Okay, so let's look at who is our nucleophile in this case. If we're breaking here, this is our nucleophile here. Let's try drawing that. So on one side, it's the methyl group, and on the other side, it's, the nucleophile that was there. But now, from here, 1, 2, 3, 4, 5, 6, we have to go, this is still attached, even though we broke at the orange line, we have to go 1, so 1, 2, 3, 4, 5, 6. Right, 1, 2, 3, 4, 5, 6. Right, so this would be our nucleophile, and it would make an intramolecular cyclization to the ester and boot off the, right, and remove the ester group. And this is a thermodynamic enolate. So to get this to go, we would need to use an unhindered base or a weaker base. There we go. Now, these are a few book problems. I'm going to leave you to do those, and we can maybe go over them during our Zoom session. And that is it for part 1 of condensation reactions. We covered aldol, cross and directed aldol, claisen, same thing as aldol but with esters. We did intramolecular of both of these and combined aldol and claisen reactions.